Okay, so my problem was from homework number 2 to number 26. So here I already have like the problem statement, the equation required, the knowns that you could just derive from the problem, and like a visual aid to understand what's going on. So the problem asks a positive 12 NC charges at the origin. What are the electric fields at the positions of 5 centimeters and 0 centimeters, negative 5 centimeters, 5 centimeters, and negative 5 centimeters, and negative 5 centimeters? So to easier understand that, I drew it out. So here we have our y-axis measured in centimeters, our x-axis measured in centimeters, and this would be our charge at the origin again, and it's positive 12 NC coulombs. And then I just put our 5 centimeters and 0 centimeters. I denote that as A here, so it's at 5, 0. B would be at negative 5 and 5, and then C would be at negative 5 and negative 5. And then since B and C have X and Y components, I just already went ahead and drew that out. So since 5 and 5 are equal, this will be an equilateral triangle. So then this would be 45 degrees. And so with this one here, so then we already know that the X component of the B point, that the electric field can be, just using some trig, it can be derived that it'll be a product of the cosine 45 degrees and the entire electric field at B vector. Okay, and then the equation I chose is this one because given what we already have here, we have the distances of R, we have the Q is just a constant, and we have the charge to solve for the electric field, which is what the problem's asking for to begin with. So now at this point we just have to do calculations at each point. So first I'll start off with point A. So point A is easy just because it's only in the X direction. Sorry, it's out of focus. It's only in the X direction, so we have to do it once. So it's going to be this equation. I'll write that again over here. And then when you plug in K for the constant, which is 9 times 10 to the 9 newtons meter squared over coulomb squared, you get, and then once you also plug in, oh yeah, okay, so once you just plug in that, you're going to get 108 n squared over c. Oh, and then when you already plug in the charge as well, since the charge will be consistent throughout the whole problem, you get this over your r squared, and then once you plug in the r squared for this scenario of this, which is just 5 centimeters, which is 0.05 meters, it'll look like this. 108. These will cancel, and then again, since this is in the X direction, or I hat for the note to keep the notation consistent, to keep it in component form, the answer for this one will be 4.3 times 10 to the 4 for C. So this would then be the electric field at point A. And then for point B, there are again 2 components, so we just have to do this 2 times, or no, we could just do it all in, since we can do the law of superposition, we can just do the electric field at B is equal to the electric field B in the X direction plus in the Y direction, and then once you plug everything in, again, using these derivations for this, for the X part, you will get negative, because it's we decided that this is a positive Y direction, this is positive X direction, and B is clearly in the negative X direction and the positive Y. It'll be in the negative E cosine 45 degrees I hat plus the positive EB sine 45 degrees J hat. And then all we have to do, like, we can see that this repeats itself, so we can just bring it outside so that's easier to not make any algebraic mistakes later. And then cosine of 45 and sine of 45 are the same thing, it's just 1 over root 2. And then what's left is just our negative I hat and j hat. So then we could just plug in for here, which would be 108 n squared over c all over, and then using the Pythagorean theorem, we can just use the length of this and this squared to get this squared. And since it has to be squared anyway with the equation, we don't have to like do any other algebra. We can just plug in the x component squared and the y component squared. So it's going to be negative 0.05 meters squared plus 0.05 meters squared, and then just bring the rest of this down. So that'll be 1 over root 2 and negative I hat plus j hat. And then ultimately we will get negative 1.5 times 10 to the 4, excuse me, I hat plus 1.5 times 10 to the 4 j hat nanometers per coulomb, because these cancel. And then, so that is our electric field at point B over here. So now we'll find the same thing for C. But for C, it'll be the same exact process, except as you can see, it's exactly the same except in the negative direction for its y. So we can just write it like so, mirroring this one, except changing this positive into a negative. Negative 1.5 times 10 to the 4 I hat minus 1.5 times 10 to the 4 j hat. C. And then part B asks to draw a field diagram showing the electric field vectors at these points. So I went ahead and drew in the electric field vectors. Basically, they're just going to be going in the same direction away from the source charge since it's positive, stated in the problem originally. And since we solved for the electric fields, we knew that this was just in I for A, so I just drew in the x direction. And for B and C, again, we knew that there was an I and j component. They're going to be like the same magnitude, but just in opposite directions in terms of y. Yes, okay, so that's the whole problem.